Next talk has two speakers. They are Spiros Argyros from National Technical University of Athens, Greece, and Richard Haydon from Oxford University. And they are going to tell us about Bourgain and Delbaen L-infinity spaces, the Scalar-plus-Compact property, and related problems.
So, thank you very much. It's a great pleasure to be here, and especially to share a platform with my old... What? Am I... I've got a mic. Is it... Is that better? Yes. Especially a pleasure especially a pleasure to share a platform with my old friend Spiros, who has done so much in this area. So, I'm going to hope that things work. Ah, yes, it goes twice. So, the story goes back to a remarkable paper of Bourgain and Delbaen published in 1980. A sort of theme of the talk is that a really good counterexample shouldn't be thought of as a dead end, but a door that opens on a new and enriched theory. But that sometimes takes a bit of a time to become clear. So the Bourgain and Delbaen construction, as we see it now, was there, and we were greatly in awe of it for a long time, but it was about 20 years before we saw how to use it in another way. What I want to talk about today is how Spiros and I were able to combine that with ideas of Gowers and Moret and their famous hereditarily indecomposable spaces to solve an old problem that was called the Scalar-plus-Compact Problem. That's to say, we created a Banach space on which every bounded linear operator was a compact perturbation of a scalar operator. So something we might as well note straight away is this means that every operator commutes. Every operator, yes, is scalar plus compact. So by the old theorem of Aronshine and Smith, every operator has a non-trivial invariant subspace. So perhaps it's worth saying, since our 2011 article, a lot of other things have happened using this Bourgain-Delbaen construction. I've put a list of some of the authors involved up there. Unfortunately, I'm not going to have time to do justice to all the new stuff that has happened. And really, for my part of this talk, I'm going to concentrate on trying to explain in a not too technical way how the construction of this scalar plus compact example works. Spiros will then take over and talk more about invariant subspaces and some more recent work that doesn't use the Bourgain-Delbaen construction. So, yes. So, before we pass on to the counterexample, let me just say that this isn't just a counterexample. The same construction has been used to prove what one has to say, positive results. There's the remarkable theorem of Freeman, Odell and Schlumprecht, which says that every Banach space with separable dual embeds in an isomorphic predual of little L1, and that's exactly an application of Bourgain-Delbaen. And more recently, we've noticed that some old theorems of Zippin can be quite nicely and elegantly approached using these methods. Again, sorry, it's for another time. Right, so the plan for the rest of the talk is going to be, first of all, we'll say what script L-infinity spaces are and what this construction is about. And then, I have to be careful not to go too far, yes. So then talk about a particular nice class of BD constructions, which I call standard. I shall briefly mention this embedding theorem of Freeman, Odell and Schlumprecht, which you have to mention that, it's so nice. So then, I've said that our construction builds upon two things. One was Bourgain and Delbaen, and the other was all the material that went into Gauer's counterexamples and the Gauer's-Moret theory. So I've got to say something about that to see how it's going to fit in. So that will mean talking about Tyrrellson spaces, and I say few operators constructions. That's a quick way of talking about the Gauer's-Moret theory. So then I'll talk about, then it's going to be this space xk with very few operators. That's another way of saying scalar-plus-compact. And then I'll hand over to Spiros to talk about the invariant subspace property in much greater generality. So, here we go. So what are script L infinity spaces? These go back almost exactly 50 years to some lovely papers of Lindenstrauss and Pelczynski in the late 60s. And these are papers which introduced what became known as the local theory of Banach spaces, the fact that you can, under some circumstances, say a lot about the global linear homeomorphic theory of an infinite dimensional Banach space just by conditions on its finite dimensional subspaces. So here's, come on, yes. So here's a more precise definition of what a script L infinity space is. It means that there are a very rich class of finite dimensional subspaces which, up to a constant lambda, are just finite dimensional spaces with the little L infinity norm. So just to say, M isomorphic, two Banach spaces are M isomorphic if there's an invertible linear operator between them, call it T, such that the norm of T times T to the minus 1 is at most M. So it's a measure of how far apart they are. And if you wanted to know what was the definition of a script LP space, you just replace the infinity with P. So, in the separable case, you can obviously arrange that your finite dimensional subspaces are nicely nested, so they form an increasing family whose union is dense, and then each one is M isomorphic to the finite dimensional an infinity space of the right size. So here we are. We have embeddings like E1 into E2, and these it makes us interested in what are nice embeddings between finite dimensional infinities. So a particularly nice way of embedding one L infinity space into another is by a linear extension. I'll start off by talking about pure algebra, so there are no norms here at the moment. So notation, r to the gamma is what you expect. R to the f, when f is a subset of gamma, is what you expect. This is French notation. I think r to the brackets gamma, it's the finitely supported ones. And in our applications, usually the elements of r to the brackets gammas are thinking of as functionals, whereas the elements of r to the gamma we're thinking of as vectors. And we use I use a rather babyish notation to represent that. Things that I think of as functionals, I give a star to, and vectors don't. And this means that there's some ambiguity. If you take the usual unit vector, which has got a 1 in the gamma slot and zeros everywhere else, you can think of it either as a vector or a functional. So when I'm thinking of it as a functional, and it is of course the evaluation functional, I'll give it a star. Right. So here we are. We've got an increasing sequence of finite sets now, and their union is called gamma. Delta the different sets. And just suppose that for each gamma in a delta n plus 1, we fix some functional that's supported on gamma n. So if you think of the deltas as being delta 1, delta 2, delta 3 moving to the right like that, it means that C star gamma is supported to the left of gamma. So what can we do with those? Well, we can use them to define an extension. If you have a function defined on gamma n, we can extend it to gamma n plus 1, and if it's an extension, of course, you don't change it on the set gamma, but on the different set delta n plus 1, you use the functional C star gamma to do it. So there's nothing very deep about that. Then, of course, you can keep going. You can keep composing and composing and composing, and you end up with an extension to the whole of gamma. And then we have some little algebraic conditions that such things satisfy. So, whoops. So you notice the images then form an increasing sequence of finite-dimensional subspaces of R to the gamma. Remember, we've got no norms at the moment. This is just linear algebra. And we've got some projections from the whole of R to the gamma. You've got a function on the whole of gamma, you restrict it to gamma n, and then you extend it, you get a projection onto these things. So, right, where are the norms going to come in? Whoops, oh no, norms not yet. Okay, so here are a bit of elementary linear algebra. I think that we can not pay too much attention to this except for, ooh, that wasn't supposed to happen, come on. Yes. I think that this notation is important for what follows, that we define d gamma to be the extension of the unit vector at gamma, if gamma is at stage n, and d star gamma is e star minus c star. So let's press on. Now the norms come in. Suppose that by some remarkable luck, all of those extension operators take values in the bounded functions on gamma, and that there's a uniform bound on their norms going from L infinity back to N infinity. Yeah, a lot of good things happen. And in particular, then your fn's turn out to be m-isomorphic to the L infinity n's. And so the subspace X, if you take that to be the closure of the union of the fn's, it's a script L infinity M space. And moreover, these D star, I said the only thing to remember from a previous slide was the definition of D star gamma. They form a Schauder basis of little L1. The biorthogonal vectors, D gamma, it turns out that I've probably already said, yes, the D gammas defined in terms of the extensions are exactly the things biorthogonal to the D star gammas. They form a Schauder basis of X. And the projections are all fine. So everything is wonderful. So that's the most general version of a Bourgain and Delbaen construction. So briefly stated, a Bourgain and Delbaen space is a script L infinity space obtained from a chain of extension operators. Well, I have to mention a result that surprised me. My co-speaker, plus Gasparis and Motakis, they remarkably showed that every separable L infinity space is isomorphic to one of these. So you might think that extension operators, they're really special and unusual things. In this sense, they're universal. On the other hand, at this level of generality, okay, you have a theorem that says everything we can ever have is got like this. Unfortunately, it's not easy to carry out explicit constructions because you don't have a condition on the C stars because basically the data you're going to put into a construction are going to be the C stars. We don't have we're a million miles from having a necessary and sufficient condition for these to guarantee the boundedness. So fortunately, Bourgain and Delbaen had already dealt with this problem, and so we're going to now take a trick of theirs and turn it into a definition. So this is slightly curious, particularly that formula. I don't think I'm going to be able to talk deeply about why these formulae work. But it turns out, if you fix this constant beta, I trust I have yes, well, I haven't given the condition on beta yet. That will be on the next thing. So these are special, let's just say these are special forms for the functional C star. So what's the good result? Evidently, what's missing is weight of beta strictly less than a half. Sorry. So here, we should say beta strictly less than a half. You can guess that because otherwise the the definition of M doesn't make much sense. Anyway, so this, suddenly we've got a way to define these things in much greater generality. So we'll call then X of gamma a standard BD space. Now this is getting to be something that is a good deal easier to think. So let's go back. I've written again the two possibilities of what C star can be. You can see that C star, in one case, it's just beta times a certain thing. And in the other case, it's evaluation at some psi further off to the left, and then you've got this beta. That's a thing, and for a while now, I've been calling psi, when it exists, the base, B star, the top, and S, the cut. You see, in some sense, this has something to do with shopping B star. Right, so to give a standard BD structure on a set, you first of all split it up into these subsets. And then you just have to define three functions. I'm trying to make it as discrete a kind of construction as possible. And there are some constraints that would have to be true. So you still have freedom to specify the weight beta, which has to be smaller than a half. And in fact, you could take the same set and the same base top and cut and vary the beta. And this is quite an interesting thing to do. You can even push beta all the way to 0. And the scale of BD spaces that you get turns out to be interesting for some of the positive results that I'm not going to talk about. So, what about duality? One of the issues with the general BD construction is that the dual could be separable, or it could be non-separable. And it's not easy just by looking at the C stars to know which one it's going to be. In this case, in the standard set, it's quite straightforward because you can equip gamma with a tree structure. And so for a given, you remember, psi is the thing that sometimes turns up in the C star of gamma. So the immediate successors in the tree structure are the elements whose base is psi. And turns out that the dual identifies naturally with L1 of gamma. It's exactly if there isn't an infinite branch in this tree, so that's called being well-founded. And so in what follows, we'll mostly be trying to look at cases where the tree is well-founded. well-founded trees have countable ordinal indices, and in the more subtle theory, that becomes important as well. So briefly, I'll mention this wonderful embedding theorem, which is inspired by the elementary fact that we all learn every separable Banach space is isometrically a quotient of little L1. And what they showed is that if Y is a space with separable dual Y star, you can embed Y into some X whose dual is isomorphic to little L1. And then, of course, the dual mapping of that embedding is a quotient operator from X onto that. So we can, just tinkering slightly with their result, you can get that result. And to give an idea of the proof, you can take a particular epsilon net in the unit ball of Y star. You choose it rather carefully in such a way that you can actually define the operations base, top, cut, and with a suitable epsilon, the same epsilon, you take the resulting BD structure. So, pressing on. So I said at this stage, I'd have to say something about Cyrilson spaces and how they are used in constructions of Gowers-Maury type. So, okay, let's go for it. If you were looking for another example of a counterexample that, after a little delay, opened the doors to wonderful new theories, you couldn't do better than Cyrilson space. But of course, when you first see it, you think, oh, this is just a counterexample. It says that what we were trying to do, which was embed little LPs or C0 into Banach spaces, can't be done. But actually, it turned out in the longer term that Cyrilson space and its generalizations were essential for the next step in Banach space theory. And essentially, everything that has to do with what we now call asymptotic finite-dimensional theory of Banach spaces comes back to this. So, okay, so he's going to define a norm on R to the n in brackets, so it's finitely supported sequences. And it's going to be a perfectly reasonable thing to do. You take the supremum over a certain subset of the inner product, F star X. But what is neat is the way the subset is determined, and you can think of it as being given by recursion or as a fixed point. Anyway, here is the definition. You make sure that your subset, first of all, it contains plus and minus all the unit vectors. That's reasonable enough. And then you demand that it's to be closed when you take a special sort of linear combination. And the conditions on the linear combination, well, those have to be in W. That's an innocent condition. This condition, that's the condition that we usually say that the F star Ks are successive, that the support of one lies to the left of the support of the next one, or else you can call them a finite block sequence. Both these words are in action. However, the interesting condition is that one, which says that the number of blocks you're allowed is up to n if the first one starts at n. That was the clever bit of the Cyrilson construction. So that was the space that didn't contain any LP or C0. And then there were generalizations. shall talk about. So there's a really obvious generalization. There's nothing magic about a half here. You can replace a half with any positive weight beta less than 1. Less obviously, this condition that I highlighted, that the number of blocks should be less than or equal to the minimum support of the first one, you can replace that with saying that the minima of the supports, taken as a set, lie in a certain kind of family of finite subsets of n. And these are called regular families. The definition of a regular family of finite sets, it has to be compact in the pointwise topology of 2 to the n. And then you also want it to be what they call spreading. That means that if you've got one set in the set, and you push all the elements off to the right, that's still in the set. Okay. The next stage, this was a real breakthrough, because the next stage, at first sight, it doesn't look as if this is going to be a terribly interesting thing to do, generalization for its own sake. Oh no. Okay, so what you can do is allow a sequence of distinct weights, and with associated regular families mi, typically the beta i's get small and the regular families get big. So there's a playoff here, and you get a thing called a mixed Zerelson space. Well, the reason why this was not an idle generalization was that Schlumprecht's space, presented in about 1990 as an arbitrarily distortable Banach space, it was of this type. And it was that discovery which set off the whole Gauer's, all of the Gauer's counterexamples and this Gauer's-Moret program of HI spaces, which was then so successfully pursued by what I shall call the Athenian school. So, right. I have to say a little bit about why these are so useful. That's essentially what we do. So, what happened with the original Zerelson space? Every normalized block sequence of vectors was actually equivalent to something that you already had with the unit vector basis. That's not the case with mixed Zerelson, and in a sense, that failure is what makes them so powerful. So however, there were special sequences, always called RIS, which have originally stood for rapidly increasing sequences, for which those upper estimates held. It's a rich class in the fact that every infinite dimensional subspace contains such a RIS. So how does that help construct interesting counterexamples? Well, the counterexamples that you got in the Gauer's-Moret theory had what are called few operators. So that's to say they were perturbations of lambda identity by a strictly singular operator. So strictly singular operators, it's a class bigger than compact operators. And they're characterized by that. People may know that these are the operators which preserve Fredholm index. So in a typical construction of this kind, you proceed as if you're going to make a mixed Zerelson space, but you add some extra restrictions on quite what the FNs are that you admit. So this uses, using a coding method which you can trace back to 77, you can do this in such a way that every operator on the resulting space, and for every RIS, the norm of T xn minus lambda xn tends to 0. But every subspace contains a RIS. So there's no subspace on which the thing is an isomorphism. All right, so now I'm getting perilously close to well, my watch, to the end. So what we are aiming at is the scalar-plus-compact property. And that's replacing the K of the S of strictly singular with a compact. Now, that is necessary because it was shown that on Gauss-Moret spaces, there are strictly singular non-compact. So to do this, we're going to have to go back to the BD construction, and it will turn out that in the BD construction, by a miracle, which I'm not going to have time to talk about now, because I misjudged the length of my part of the program, there is a miracle which means that every strictly singular operator is compact. I'm sorry that I've already overtaken my time a little bit. I'm going to hand you over to Spiros, who's going to talk about invariant subspaces. So I'm going to skip through and I get to there. Over to you, Spiros.
Let me add one thing. When we discuss about exotic Banach spaces, always think that these spaces have a very, very strange norm. But from what Richard explained, one of the miracles with Bourgain and Delbaen construction is that the norm on these spaces is the natural one, I mean the supreme norm coming from L infinity of gamma. So there is no problem concerning the norm. The problem concerns essentially the structure of the elements. Okay, and one more thing, excuse me. One more thing is that when we deal with a Banach space X, and we want to impose some properties on the space X, strange properties, then right now we have a machinery that we can do it, I mean, in the most of the cases. But if you deal with the space of the linear functions, bounded linear functions on X, and you want to impose properties to construct X such that L of X has certain properties, then this is somehow ad hoc method. I mean, we do not have a real general method constructing spaces with such a property. For example, it is not true and it is not correct that if you consider any scriptal infinity space which is hereditarily decomposable, like the example we have with Richard, then automatically the operators have the scalar-plus-compact. This is an example constructed by Talbot. And this shows that these two properties, scriptal infinity plus hereditarily decomposable, does not yield necessarily the scalar-plus-compact property. Now, let me move now to the other topic very shortly. I mean, I'm going to discuss a little bit, sorry, but I cannot see. I'm going to sit a little bit. Okay, here it's better, I think. I'm going to discuss about the invariant subspace problem, which is, first of all, let's see what is, when an operator has invariant subspace, non-trivial invariant subspace, that means that there is a closed subspace, which is non-trivial, meaning that this subspace is not zero, it's not the whole space, such that the image of this subspace is included in the subspace Y. Okay. Well, the problem is the following, that we start with a Banach space X and of infinite dimension, of course, and an operator acting on X, and the question is, does always the operator T admits a non-trivial closed invariant subspace? Okay, this is a problem, this is a problem which remains open for Hilbert spaces, And on the other hand, in the case of Banach spaces, there are a certain class of operators. First of all, there are certain class of operators which have this property, and also in the case of Banach spaces, we know much more. And I'm going to explain a little bit, first of all, the positive results, meaning what kind of operators have invariant subspace, and secondly, some negative results. Okay, the first result mentioned already by Richard is that the compact operators have invariant subspace. This goes back to Argyros and Smith. The important result comes from Lomonos, where he proved that if you have a non-trivial operator, then which commutes with a compact operator, then actually it's going to have a non-trivial hyper-invariant subspace. Hyper-invariant means that this subspace is invariant for any other operator which commutes with T. And there is an extension of this result by Hooker and Sirotkin for operators on real Banach spaces. I mean, Lomonosov result is for complex Banach spaces. And for real Banach spaces, then the operator must satisfy the relation written in the last line. Okay. Now let's go to the negative results. The famous negative results coming from Enflo and then from Reed, that their paper published, I mean, Enflo paper published a little bit later than Reed paper, but Enflo announced his result first. And they present examples of operators on Banach spaces which fails to have a non-trivial invariant subspace. And furthermore, Reed did much more work, and he proved, I mean, a remarkable result that if you start with any Banach space, I mean, Enflo and Reed construction was concerning the construction and concrete Banach space and an operator on that space. Now, Reed proved the following, that if you have a Banach space that contains C0 or it contains complemented little L1, then actually on such a space you can construct an operator without invariant subspace. Okay, for C0, we know that it's separably ejective. Therefore, if you say that a separate Banach space contains C0, then contains C0 complementarily. For L1, the assumption that L1 is complemented in the space is necessary since by a result with Richard and Raikov-Salis, we have proved that there is a Banach space, scriptal infinity of course, with Scalar-plus-Compact and contain little L1, but there L1 is not complemented. Therefore, if you remove the complemented hypothesis from Reed's theorem, then the theorem is false. And also this is an important result explained by Reed that you can construct a strictly singular operator which does not have an invariant subspace. You see, strictly singular operators are very close to compact ones. Therefore, this result is a rather impressive result. Okay. A Banach space has the invariant subspace property if every bounded linear operator admits a non-trivial closed invariant subspace. And as it was explained by Richard, and it has the hereditary invariant subspace property, if every closed subspace satisfies the invariant subspace property. Okay? Now, as was told already by Richard, is that spaces with the Scalar-plus-Compact property from Argyros and Smith theorem have the invariant subspace property. And therefore, the first example with the invariant subspace property is the space constructed with Richard. And on this space, we don't know if the space has the hereditary invariant subspace property, because the scalar-plus-compact in the scriptal infinity does not remain true for the subspace of that space. I mean, if you go to the subspaces, then actually these do not have the scalar-plus-compact property. Now, the scalar-plus-compact, the scalar-plus-compact problem remains open for reflexive spaces. I mean, Richard explained that it is really important to deal with a scriptal infinity space, but scriptal infinity spaces are not reflexive. And moreover, there is no known example of a bounded operator acting on a reflexive Banach space with no non-trivial closed invariant subspace. And this is also a great problem. And the reason is that we know from Argyros and Smith that compact operators have invariant subspace. And the question is that if you substitute the compactness by the weak compactness, if this property remains true. I mean, we don't know how important is the weak compactness in the case of operators. For example, weakly compact operators, we don't have any example of a weakly compact operator without invariant subspace. Okay, and recently in a joint work with Pavlos Motakis, we have constructed a reflexive space with the invariant subspace property, and this is the first example which has the hereditary invariant subspace property. I'm going to tell you a few things about this space. This space is a reflexive, hereditarily decomposable Banach space. For every subspace and for every operator on the subspace, this operator is multiple of the identity plus a strictly singular operator. It's therefore, this is what we use also in the case of scriptal infinity, hereditarily decomposable. And the important property is that if you consider any two strictly singular operators on this space and you take the composition of them, then this is a compact operator. And the last thing, this is because someone could ask that is it possible, I mean, to this space to have the scalar-plus-compact? No, it does not have it. And in every operator, you do not, in every subspace, you do not have it. The reason is that the space of operators on every, of strictly singular operators on every subspace is non-separable. I mean, the compact operators on this space are separable. There are an enormous number of operators which are strictly singular and not compact. Therefore, condition 2 is really important. I mean, that the composition on any two operators is. Every Banach space satisfying 1 and 2, meaning that it has this, every operator is multiple of the identity plus a strictly singular operator. And also, probably I have 1 minute or 2 because we have the problem with the machine. Thank you. Every Banach space satisfying 1 and 2 also satisfies the hereditary invariant subspace property. And this is easy to explain because here is the importance of Lomonosov theorem. Because the square is compact, that means that your operators commutes with the square of the operator, and therefore from Lomonosov theorem and Hooker-Sirotkin extension in the real case, you have the property. And the other interesting thing about this space that if you look at the Calkin algebra, this is the quotient of the operators over the compact operators. This is non-separable, and the interesting that in the Calkin algebra, the product of any two operators is 0. And this somehow this was used by Skillicon to prove that the Calkin algebra admits at least two equivalent, non-equivalent, complete multiplicative norms. And okay, I will stop here. Thank you very much.
Okay, thank you very much. Are there any questions, comments?
Yeah, Richard, come with me.
So I would like to know if there are infinite dimensional Banach spaces with the nuclear plus identity property?
No, this
We don't know.
this is an open problem, and we don't know what's the answer in that problem. This is, yes.
But it's
Yeah, I mean, we cannot say even as a conjecture if there exists or not.
it will need completely different ideas from these.
Still open.
Yes, so my question is about the invariant subspace problem for separable Hilbert spaces. I just want your opinion. What do you think is the challenge? What is the problem? I mean, despite the fact that separable Hilbert spaces are well understood, I mean, they're pretty simple, but, and what's your guess that it would be true? What is your hunch?
Yeah, first of all, this is what I mentioned in my presentation, is that there is the weak compactness. I mean, every operator is weakly compact clearly in a Hilbert space because Hilbert space is a reflexive one. And it is not clear yet how important is weak compactness for the invariant subspace property. So I cannot guess what the answer will be. If we have an example on a reflexive space, then probably we can guess more. But right now we do not have anything, so remains dark what's the role of weak compactness in the invariant subspace problem.
So unlike the other problems like the Riemann hypothesis, people tend to think that it's probably true. So, and with this it's not so clear.
For me, at least for me, I don't know if Richard has something different. I cannot say.
Thank you.
Any other questions? If not, let's thank Spiros and Richard again.